Well, thank you very much, everybody, for coming. Today, I'm going to be talking essentially, I mean, despite the title of my thesis being Constrained Learning and Inference, I'm going to be talking about constrained learning. I covered constrained inference during my proposal, and I'll go back to that at the end just to talk about some new developments, but the bulk of my talk will be about constrained learning. So when I say learning, I mean obtaining solutions for statistical problems based on data rather than models or distributions. So that's in contrast to inference, where we have a model or a distribution from which we want to extract solutions. That's not to say that we can't use models for learning and get some hybrid methods. It's just that that's not the core problem in that setting or in that approach. Right? Now, as a technology, learning has become ubiquitous, mostly because the complexity and the scale of problems that we want to solve today is so large that make first principle solutions hard. And at the same time, we have very easy access to data nowadays due to the lowered cost of sensing and networking technologies. But as learning has reached critical applications, such as social, industrial, or medical, its shortcomings have become very obvious. And this has been evidenced by a growing number of reports of failures of learning from biased, prejudiced models to fatal accidents even, right? So there is a need today to curtail the behavior of learned solutions so that we can use them in applications where failure is more costly than simply showing the picture of a cat when somebody searches for a dog. So what we need today is not really to learn, but to learn under requirements. So in other words, we want to obtain a solution from data, but not any solution, right? And the goal of my talk today is to basically show you that constrained learning is the right tool to enable learning under requirements, and that even though it is a quite challenging problem, it is not impossible, right? So let me start with the first point, which is basically how do we enable learning under requirements? So today, there are basically two ways to learn under requirements. The first one is to exploit the model structure. So we construct models that embed the requirements such that they meet the requirements essentially by design, right? So this is very common in geometrical applications, such as having rotation invariances or aliasing invariances, or for shape constraints such as monotonicity, right? The problem is that constructing these models that meet these requirements is very hard. It is very time consuming. It requires a lot of domain knowledge. And sometimes it's very complicated because we have models nowadays that are very opaque, that have large and very opaque, such as neural networks, for example, where the relationship between the parameter and the output is not really clear. So this is hard to do, and also to combine different types of requirements, especially if we want requirements, statistical requirements like fairness or robustness. If we want a model that is fair and robust, that is much harder to design than a model that is fair or robust. So an alternative is to use regularization, which is an ubiquitous technique. That is basically, the idea is that we encode these requirements in penalties that we add to the objective, basically, of the training of our model. And the advantage of this technique is that they are very easy to combine. We want an additional requirement, we just add a new penalty, and it doesn't really change the way we train. It's just simply the exact same optimization method or whatever other learning method we are using. The problem is that this method is not guaranteed to meet the requirements. The solution, this depends a lot on the penalties that we choose, on the weights that we choose for those penalties. And there may not even be penalties and weights that actually give you feasible, good solutions, right? So constraints come as a more natural solution to this problem, because requirements in the first place, engineering requirements, are often expressed as constraints, right? When we are using exploiting the model structure or the regularization or the objective, we need to first encode these constraints into either models or penalties in order to use them. Now, the other advantage is that they are guaranteed to meet the requirements, because by design, that is what constrained learning does. And it has an additional advantage, that it decouples the performance from the requirements. So in the case of exploiting models or model structure or regularization, it's very hard to tell how much the requirement, what's the cost of the requirement on the loss, or which requirement is harder to meet, which is something that we can do when we use constraints. The issue with constrained learning is essentially that is really hard to do, basically, right? So in order for me to go into why it is hard, we need to start by formalizing basically what I mean by constrained learning. Right? So the classical unconstrained learning problem, in this talk at least, we're going to see it as a optimization problem, a statistical optimization problem, where we want to minimize the expected value of a loss. And constrained learning is the exact same thing, except that we add constraints. And I will talk about two types of constraints in this talk. Basically, we will consider constraints that are on average, that are expectations, bounds on the expectation of the value of a loss, and constraints that are pointwise, where instead of holding in expectation, the constraints need to hold almost everywhere. Right? Now, constrained learning problem inherit from learning problems two challenges that get combined or composed with the challenge of doing constraint optimization. So the first one is that these are infinite dimensional problems. We are trying to find functions, and functional problems are infinite dimensional, which is something hard because we do not compute in infinite dimensions. And the other one is that we do not know the distributions against which we want to compute these expectations. Right? We only have access to samples from those distributions. Now, one idea that is the first idea we might have is to do exactly what we do for unconstrained learning in constrained learning, which means that we're going to tackle these problems in two ways. We're going to exploit a parametrization. So we will find a finite dimensional parametrization of this functional space. So for example, if we are talking about the space of continuous functions or an RKHS of some sort, we can be talking about a parametrization that is a neural network or a finite combination of kernels, right? A linear combination of kernels. So this is the first approach. The second one is to replace the expectations by their empirical approximations, by empirical averages over the samples that we have. Now, the advantage of this is that we obtain now a problem that is both finite dimensional and deterministic. So it's a problem that technically we can solve. And it turns out that in the unconstrained case, we know that the solution of the problem on the right gives us a solution of the problem on the left. Essentially, we can solve a deterministic finite dimensional problem and obtain an approximate solution of this statistical problem. This is classical VC learning theory. That does not hold true anymore once we add constraints. VC learning theory only talks about unconstrained. So we don't even know if this deterministic finite dimensional problem, if we could solve it, we don't know whether we would get a solution of the problem we actually care about, which is the problem on the left. Additionally, this is a constrained non-convex problem. The finite parameterizations that we use typically lead to non-convex problems. And while that's not a big deal in unconstrained, in the unconstrained case, because we can use some sort of dynamics like gradient descent, and there's good empirical and even theoretical evidence that we can get to a good local minimum. That's not true for constrained problem. Even finding a feasible solution, not even a good one, a feasible solution for this problem can be as challenging as solving the problem itself, right? So interior point or barrier methods, not very appropriate in this case, or hard to apply, at least in general. So what we might think of using is duality. That is a way to transform this unconstrained problem, this constrained problem, into an unconstrained one. And that one we sort of know how to tackle. The issue with non-convexity is that duality doesn't necessarily, this unconstrained problem doesn't necessarily give us a solution to the original one. And that goes beyond the fact that we cannot solve it from an algorithmic standpoint. There are theoretical limitations. And that's sort of, I want to go a little bit into this because I think this is an important point here of, this is a big barrier into solving constrained learning problem. And one of the ideas that sometimes come up is that, okay, just replace the constraint problem by a regularization problem. And it turns out that that's not the case. It is not the case that constraint and unconstrained optimization are equivalent in that sense. We may not have regularization parameters, hyperparameters, that actually gives us even a feasible solution. That requires something known as strong duality. Now, we are spoiled in convex optimization in that strong duality usually holds. So this is not really an issue that we need to think about, but that is a problem when we go to complex optimization. The second issue is to say, okay, well, suppose that I have strong duality. Well, still that doesn't guarantee that if we can get a dual optimal solution, we get a feasible one. That's just a guarantee on the values of the problems. So even recover a feasible solution from the solution of the dual is not a given that that could happen. But another thing we might say is that, okay, it doesn't matter because I'm going to use a primal dual and it's going to give me a KKT point, and that's guaranteed to be, say, feasible. Yes, but a KKT point might be feasible, but it's not even necessarily a local minimum in the case of non-convex problem. That requires, it is only sufficient in the case of convex problems. So actually we have here an issue, which is that we have a problem that we wish we could solve, this deterministic finite dimensional problem, but actually we can't really solve it. And even if we could, we're not even sure that we would get a solution to the original problem we have. So it would seem that actually this is sort of a pointless way to go through learning under requirements in a sense, but it turns out that actually we can do it. We can actually use this dual problem to solve the original problem. And I want to start by showing you what we can do with this, with constrained learning, with this dual constrained learning, and then we'll go into how come this thing actually works when it shouldn't, right? So I have spent the first half of this talk talking to you essentially about why constrained learning doesn't work. Let's go into showing you that it actually does, and then why, right? So I want to start with an example in fairness, right? So the idea here is that we want not to have a classifier, but a fair one. So for example, suppose that you wanted to predict if an individual makes more than $50,000 a year based on some socio-economical data, right? So gender, occupation, education, things like that. Now, due to biases in the collection of the data and structural biases in society, what happens is that women in the data set that we have end up, the rate at which women make more than 50K is much lower than the rate at which men make 50K. So the average over the whole population is around 23%. Women are close to 10%, whereas men, the rate is close to 30% of men, right? What happens is if we just learn a solution based on that, just learn a model to predict whether people make more than 50K based on that, the model picks up on that bias and naturally replicates sort of the bias that exists in the data set. So what we want to do is not to predict if an individual make more than 50K, but we want to do that without discriminating based on gender. So this is the fairness constraint that we want to impose in a sense, right? And the first idea might be, well, why don't you just remove gender from the data set and just build a model without looking at gender? And it turns out that that does absolutely nothing, because in the data, gender is highly correlated to other variables that exist. And therefore, the model can still pick up on sort of this gender bias through proxies, essentially. So this is not a solution that works. So what can we do? Well, an idea of what we can do is pose a problem where we want to minimize the error, the performance, the accuracy of the model, right? But we want to make it invariant, in a sense, to gender. So whether we have a person that is a male, if we flipped their gender to female or from female to male, it shouldn't change the prediction, essentially. This is known as the average counterfactual effect. So we want a bound on that. We can be even stricter and impose that in point-wise. So it has to hold not on expectation, but for each element of almost surely over the data set. And if we solve this problem using the techniques that I will show later, we get exactly what we asked for, which means a classifier that is invariant to gender, essentially, right? So the change in prediction in the unconstrained case was close to 8% of the cases. It would change from 1 to 0 or 0 to 1. And if we impose the pointwise, there are 4 elements of the data set that change, essentially. And so we are able to really constrain. And another thing that we get out of this is what I mentioned in the beginning, which is this idea that we can now explore which of the requirements are harder to meet, which in this case, or the case of the pointwise constraint, is which of the persons in the data set, which of the individuals in the data set were harder to make invariant to gender, right? So we can look at the phenotypes now, at the features, and see which features are harder to to actually make invariant, right? To make fair, let's say. And if we look at that, we see immediately that we have a population. The hard ones to make invariant is a population that is mostly non-white, married, of non-US, and with master's degree. Right? So immediately this should look odd, because it would seem that there are other variables that are highly correlated with gender that still sort of carry the same information. And actually that is exactly what happened. Even though our classifier is now invariant to gender, it still is not fair in the sense that it gives as much, the prediction is not the same for genders, for different genders, right? That is true for the average, and that is true for the pointwise as well. So what happens here is that the classifier did exactly what we asked for. It became invariant to gender, but if what we wanted was actually to overcome these biases in society, instead of just becoming indifferent to them, then that's what we should have asked for. And we can actually do that. We can say that we want a classifier for which the rate at which we predict more than 50K for male and female is within 1% of the overall rate of the population. And if we ask for that, which is a stronger requirement, is a parity requirement that is stronger than the invariance, then we get exactly what we did, which means we get a constraint classifier that now has essentially the same accuracy, 82% compared to 83, essentially the same accuracy as the unconstrained, but is now fair in the sense that it predicts for male and female essentially the same rate. Right? The same thing happens, this is not an exclusive to gender problem. If we look at a problem where we are trying to predict if an individual will recidivate based on race, well, the exact same thing, without discriminating based on race, the exact same thing happens, because in recidivism, race is the source of biases, right? And we can pose the exact same problem we did for gender and recover a data set that actually, a model that actually has essentially, again, the same accuracy, but that is much more fair in terms of the rate at which it predicts for different races recidivism, right? Okay, so this was an example in fairness. It would look that for fairness, this seems to work. Is this a property of fairness itself, or does it go beyond that? This is the question that we need to ask. Or was it just a fluke in a sense that constrained learning ended up working here? And so we can look at the case of robustness as an alternative. So we want to train an image classifier, essentially. And there are very good models for that. We can use, for example, a convolutional neural network and get results that are accuracies that are above 80%, above 85% even, very easily on some quite large data sets, right? The problem with these classifiers is that if we perturb the input for very small perturbations of the input, 1 to 4% of the full scale of the pixel in this case, essentially the accuracy of the classifier drops to 5%. Now, these are not random perturbations, these are design perturbations, but still, this means that very small perturbations of the input can simply ruin the accuracy of our classifier. So we want to train an image classifier that is robust to input perturbation, not any one of them. And we can write that problem as well as a constrained learning problem, where we want to minimize the error that we make on the nominal distribution, on the normal images, subject to the error not being very large on the perturbed distribution, on the adversarial distribution, right? And if we do that, we get classifiers that are actually much more, whose degradation, let's say, with perturbation is much smoother, and they are able to essentially trade off this, the performance at, essentially at the nominal distribution at 0, no perturbation, with the performance in higher levels of perturbation. So, okay, so it seems that constrained learning, even though I spent the first half of this talk telling you that constrained learning does not work, it seems that it does. And the question now that we need to answer is how. And that's basically what I want to do for the final part of this talk, where this how actually breaks into 3 questions. So we need to talk first about what does it mean to solve this problem. This is a non-convex problem, infinite dimensional. This is an infinite dimensional statistical problem for which we do not know the statistics. So we can't really expect to get an exact solution here. So we need to talk about are we going to consider as a good enough solution? And the second question then becomes when, if at all, is it possible to actually obtain such type of solutions? And this is sort of about us trying to build a constrained learning theory akin to what happened with classical learning theory, right? We want to build that. And finally, because there are these problems now that we need to overcome in terms of non-convex constraint problems, is there actually a practical learning rule? In this case, just as we have a practical learning rule for the for constrained learning, which is empirical risk minimization for unconstrained learning. Okay, so in terms of what does it mean to solve this problem, we're going to talk about we're going to consider a good enough solution, one that is probably approximately correct constraint solution. So what that means is that with high probability, the solution, the value of the solution is close to the optimal value. So it is a near optimal solution with high probability. Now, this is related to the concept of pack learning, which is the unconstrained version, let's say, of learning theory. This is the form that we learn in the unconstrained case. Now, in the constrained case, we need additionally to have approximate feasibility as well. So we need to be approximately feasible, not only near optimal. And the joke that I like to make about probably approximately correct solutions is that they are like first year graduate students, like Juan, right? So they are not going to be really correct. They're going to be you want them to be in the ballpark of the right solution, which is approximately, and they're not going to get to the ballpark even always, but you would like that to happen often. So this is like the probably part of it. So this is the type of solution that we are looking for. That's what we can expect to get, right? So when we talk about solving this problem, when I talk about obtaining a solution, I'm talking about obtaining a PAC-C solution, a probably approximately correct constraint solution, okay? Then the question becomes, okay, when can you even do that? When can you obtain the first year graduate student solution? Well, the theorem here, the main theorem here tells us that a class of function is PAC-C learnable if and only if it is PAC learnable. And what that means is that if we can solve a learning task in the unconstrained case without constraints, then we can add requirements to it and we can still solve it. In a sense, what we're saying is that constrained learning is as hard from unconstrained learning in the learning theoretic sense, right? Mild conditions apply to this, but it's the same conditions that are required for a class to be PAC learnable, to be unconstrained learning. So essentially, these two problems are just as hard as one another. And what we need to talk about here is how, basically, essentially, right? So what we did at this point, up to now, with this equivalence and this definition, is that we removed this arrow, right? We removed the arrow that says, well, what if the problem on the right would give us a solution of the problem on the left? Well, it would. This is what this is saying. However, we still have the problem that we cannot solve the problem on the right, right? It is still a non-convex constraint problem, right? But what turns out to happen is that even though we cannot use duality here, as I said before, we can obtain a solution directly from the dual problem to the original one. So even though we cannot go through the empirical constraint risk minimization problem, we can directly go through back to the problem that we actually care about, which is the constraint learning problem. And that's actually the theme of this last theorem that tells us that under some mild conditions, I guess the biggest one of them is the fact that the losses related to the pointwise constraints have to be convex. All other losses can be non-convex under some conditions on the distribution. Then essentially the dual problem gives us a PAC-C solution of the original problem, where as long as essentially the parameterization that we use is a good parameterization in the sense that it covers well the original space of functions, right? So I want to zoom in a little bit here for us to talk about the types of errors that we make in this and relate them to unconstrained learning. Essentially, there are two sources of error that we commit in doing this approximation, this deterministic finite approximation. The first one is a parameterization error that is also known as the irreducible error, let's say, in unconstrained learning. And there is the estimation error, which is related to, the fact that we are using samples and not the distributions themselves. Now, the parameterization error here depends on the quality of the parameterization. So how good how close can we get to the original space of functions? How well do we cover that original space of functions? That is this parameter nu. But it also depends here, this is a difference to unconstrained learning, on the requirements difficulties. So the harder the requirements are to meet, which is something that is expressed by essentially the dual variables of a perturbed problem, the harder the requirements are to meet, the larger is the parameterization error. Right? Now, this parameterization error only affects the near optimality. It doesn't affect the feasibility of the problem, which is only affected by the number of samples, which is the estimation error, which essentially has, in this case, the exact same rate as in actually the unconstrained learning case. It just depends on the VC dimension, right? So these are the three things that essentially make it harder for us, or these are the three sources of error that we have in constrained learning, which are the parameterization quality and the sample size, which were already a source of error in the unconstrained case. And now, additionally, we have this idea of requirement difficulty, which means that the harder the requirements are to meet, the larger the error we're going to make in terms of the near optimality, not in terms of the feasibility itself, right? So essentially, we have answered all the questions. We have established what it means to solve a constrained learning problem, which is a PAXI solution. We have established that anytime we can do unconstrained learning, we can do constrained learning. There is nothing new. There is nothing harder about this from a learning theoretical viewpoint. And we established an actually practical learning rule, which is dual learning. So we can actually use a unconstrained learning problem in order to solve constrained learning problems. Okay? And how we do that in practice is essentially by using a primal-dual method of some sort. Right? So here, the hard part of the primal-dual is essentially to solve the primal problem here, where we have to find the minimizer of what is, in this case, a non-convex problem. Now, we don't need to find a minimizer. We can find an approximate minimizer, and that is enough for us to converge to a neighborhood of a PAXI solution. So that's good for us because we know that we can find some good approximate minimizers, good local minimizers, even for this non-convex problem, because this is an unconstrained learning problem. This is one that we have been solving for the past 20 years, or more actually, for the past 50 years. So for example, we could use some sort of dynamics like gradient descent and actually get to a good local minimum. Obviously, the number of iterations that we need to run this is very large. So typically in practice, what we do is that we do some sort of alternate minimization where every epoch, say, we will run one dual step for every epoch, for every pass over the data set. And in that case, I mean, all bets are off in a sense. The guarantees don't hold anymore, don't exist anymore. But as we have seen empirically, it does work quite well. Right? So the fact that we can solve unconstrained learning problems actually gives us a way to solve constrained learning problems. So going back to the bold claims that I made in the beginning, the goal of this talk, well, it would seem that constrained learning maybe is not the right tool, but is definitely a tool in order to enable learning under requirements. If we have access to a model that meets our requirements, for example, a model that always gives us monotonic solutions, and that's great. That is what we should go for. But in cases where this type of model are hard to get, we can actually replace the work of coming up with these models by essentially by data. Right? Constrained learning allows us to take a learning approach to learning under requirements, where we replace good models or hard work onto coming up with good models with data. Right? So this is sort of a new tool, let's say, in order to do that. We saw that constrained learning is a very hard problem. It's a constrained non-convex functional statistical optimization problem. So we have to deal with problems such as strong duality. Can we recover the primal? What are the effects of these empirical and finite dimensional approximations that we want to make onto that? So it is not an easy problem, but it is possible. And the way we solve it is the same way that we solve unconstrained learning problems, actually. We used rich parameterizations and we solve unconstrained ERM problems, which is essentially the same way that we tackle constrained learning. So that sentence that I said in the beginning, that constrained learning is as hard as unconstrained learning problem, actually goes much deeper. It actually literally is as hard because unconstrained learning problems are actually the way that we solve constrained learning problems, in a sense. So I want to conclude sort of saying, where do we go from here? In a sense, where can we move forward? A little bit. One of the things that we've been working on is this constrained learning and generalization theory. So there are a lot of papers. There are a few papers on this already. One of which was awarded the best student paper award at ICASP this year, which is on this idea of generalization theory for constrained learning. Things that we can move now is to go beyond PAC. PAC is a very simple, let's say, learning model to account for structured complexity, PAC-based, and these other forms of learning, and how they affect, especially the question of dual learning, right? And we should go also the other way. So far, we have studied a lot how learning complexity, the complexity of the class of the learning task, affects the feasibility, affects the requirements, but we can also look at the other way. How do the constraints affect the learning complexity? We now have reduced sort of the number of functions that are allowed, right? Because we have reduced the feasible set. How can we get improvements on certain, on sample sizes, for example, by using constraints, sort of that sort. So that's an interesting avenue of research moving forward. And also, I mean, the question of like the actual dynamics in order to solve these problems. So last iterate guarantees and convergence, this is a quite active topic of research. So also exploiting different dynamics, optimistic SGD and things like that. And also alternative learning rules that are not based on duality, perhaps. And before finishing, I said I was going to touch quickly on constrained inference, which is the topic that I talked more about on my proposal. So in terms of sparse functional programming, which was the main thing that we talked about in the proposal, there are some new ideas that I think are very interesting. Sparse functional programming, for example, allows us to replace Bayes rules by learning problems when fitting Bayesian models. And that's something that I think is very, very interesting. It's a paper that we wrote for Azilomar that has like good consequences, I think, to explore, and also using a little bit more these ideas into scientific applications. So I think that especially for imaging and other types of fitting that are very used in scientific measurements, I think this could be it would be interesting to exploit in the same way that we exploited compressive sensing in MRI, for example, as a good example. In terms of discrete constraints and non-submodular optimization, I think that there are a few new papers that got accepted and submitted since my proposal. But I think there is a lot of work still to be done in terms of continuous dynamics that people have been working a lot, that have moved from greedy to continuous greedy sort of things. New continuous extensions, I think this would be an interesting thing to look at. Today, the continuous extensions have these atomic measures that are used. Maybe we can exploit, find new ones that exploit non-atomic measures in order to maybe use these new tools that we have that were developed in order to solve sparse functional programs, and also new applications. I think this is a good area that we move forward. And finally, this new topic of risk-aware estimation and control that I mentioned quickly in my proposal. Actually, this is a paper that I wrote with Dionysius that also got a Best Paper Award at ICASP this year. I think there's a lot of room there to look at new estimation problems in terms of losses, constraints, and models. Actually, Tassos already started doing that, and he gave an amazing paper that got accepted into CDC this year on risk-aware linear quadratic regulators. So I think that have very interesting implications, this idea of risk-aware. So to finalize, I would like to, obviously, I mean, even though my name is on this thesis, this is not work that I have done by myself. This is, I was very lucky to have many collaborators throughout this year, and I would like to thank all of them, and thank you for coming to my defense, and thank you all the committee for also taking the time to to read through or hopefully only part of what was a quite long thesis. So thank you very much.
Thank you, Luis. Thank you.